Good morning, class. The session is being recorded. We are looking at Chapter 4, Application of Derivatives. Section 4.2, How Derivatives Affect the Shape of a Graph. We covered the first section, maximum and minimum values. Differentiation formulas. Hopefully we are very comfortable with those. The synopsis of the previous section regarding Extrema. We looked at Extrema, which refers to both max as well as mean. Absolute or global means in the entire domain, local or relative means in some open interval. So when we look at this first graph, this is a local mean, this is a local max, this is a local mean. But this local mean is also an absolute mean because there is no other point having a smaller y coordinate. Local max, local mean, local max. This local max is also an absolute max because no other point has a larger y coordinate. Local mean, local max, local mean, local max. And also I'm reminding you that the endpoints can only be absolute, they cannot be local. How do we find critical points? Simple, find f prime, okay, set it equal to 0. What makes it 0 is a critical point, and what makes f prime undefined or does not exist also would be a critical point. So having said that, if we happen to have a continuous function in a closed interval of a to b, then we can use this methodology to find an absolute max as well as absolute mean. How do we do that? First, we find all the critical points by finding f prime set it equal to 0 and figuring out where f prime is 0 or doesn't exist. Then we evaluate the function at those points as well as the endpoints, a and b. The largest value is the absolute max, the smallest value is the absolute mean, and you also want to report the location. Here's the summary of the section. A function is increasing where f prime is positive and decreasing where f prime is negative. In short, x goes up, y goes up. If you look at this, assume this is a line, looks like a line with a positive slope. In this case, when x goes up, y value goes up. This is the simplest way of thinking about this definition. A critical point was defined. You find f prime where f prime is 0 or f prime doesn't exist. Those are critical points. A relative extrema, okay, that means a relative max or relative mean occurs at a critical point at the top or bottom of an interval of a graph. A function is concave up where f double prime is positive and concave down when f double prime is negative. If double prime is positive, that means f prime is increasing. If double prime is negative, that means f prime is decreasing. Concave up, concave down. And an inflection point is where concavity changes. Okay, so it changes from one format to the next. And possible locations would be where f double prime is 0 or f prime doesn't exist. And for short, IP, inflection point. Let's discuss this further, okay, with a better understanding as to what this means. So let's quickly recap. Concave up, the graph of f of x lies above all its tangent lines on the open interval, whereas concave down, it lies below all of its tangent lines. And a point on a continuous function f of x is an inflection point or IP if f of x changes concavity. So if you look at this concave up, 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 it is entirely about above is tangent line, all of that. But I want to also add, take a look at what's happening here. Here's the slope at some point. Okay, it's the slope of a tangent line. And then here's another one. So because it's concave up, this slope is positive, but this line is steeper and it's more positive, which means what? Which means f prime is increasing. F prime is increasing, class. Okay, same thing here. Okay, if you look at this one, okay, also, although it's negative, but this one is less negative. Okay, so f prime is increasing. The second case, concave down. Okay, the graph lies below its tangent line. Okay, look at this one, look at this one. Okay, this one or this one. Okay, so f prime is decreasing. So if you look at this one, f prime is positive. Okay, but it's flattening, so it's less positive. Okay, so it's decreasing. F prime is getting smaller. Here, f prime is negative, but f prime is more negative, okay, because it's steeper. Okay, so that's the idea that we should pay attention to. Let's look at the following. How do we sketch a curve? Step one, pay attention to pre-calculus steps. So everything that we have learned, we're going to discuss that in a moment as we look at an example. After that, we are going to add relative extrema. How do we do that? We find f prime, we set it equal to 0 and solve for x, and wherever it does not exist, we do a sign graph and we make a decision about intervals of increasing and decreasing, as well as local extrema. We also find the inflection point or points. How? We set f double prime is 0, or if it doesn't exist, and we do the sign graph on that. Finally, the pre-calculus steps and the calculus steps, we put them all together, come up with the graph. It's that simple, everybody. Okay. Now, extreme values of a function are created when the function changes from increasing to decreasing, or vice versa, from decreasing to increasing. So the idea is this. The function is increasing, class, and then decreasing. So this is the location of a local extrema. More specifically, it's a local max. So increasing, decreasing, local max. This one is decreasing. This one is increasing. This is where the change is occurring from decreasing to increasing. So this is a local mean. So the extremum occurs at the point of changing. The same thing here. Notice decreasing, increasing, decreasing, and the extrema. Increasing, decreasing, increasing, decreasing. As the change occurs, we come up with the extreme values. Extreme values, local max, local mean, local max. Okay. So the theorem is a function is increasing where f prime is positive and decreasing where f prime is negative. This has been discussed, so we are elaborating on that. Now, here's a proof. You're not responsible for the proof. We don't cover the mean value theorem in this course, but just a quick, explanation as to what that means. F prime of C is f of b minus f of a over b minus a. This is the slope of a secant line that will change to a slope of a tangent line, f prime of C. This is the general idea, and the slope of a secant line is the same as the slope of a tangent line, somewhere in between. That's as far as the mean value theorem is concerned. So if you do the cross product of this, so What is the idea of increasing? Remember, a function is increasing when x goes up, y goes up. Okay, that means as we go from left to right, x is increasing, right? If y is increasing also, that is called an increasing function. So with that being the case, if b is on the right side of a, that means b is larger than a. Okay, so b minus a is positive. If f prime is positive, then positive times positive, the right side becomes positive. And therefore, the left side, f of b minus f of a is positive. That means f of b is larger than f of a. And that is the definition of an increasing. So this is the proof using the mean value theorem. I don't want you to worry about that at all. First derivative test. So y prime or f prime is positive, so the curve is rising. So it's increasing. When f prime is negative, then it's falling. So what happens? First increasing, then decreasing. That creates a local extremum, which is a local max. If it's the other way around, first is decreasing, it's falling. Then it's increasing. Again, we have a local extremum. Specifically, we have a local mean. Okay, class? Of course, y prime or f prime equals 0 or doesn't exist would be the possible local max or mean. How do we find all of this information? Using the sign graph. And again, I will go over that with a simple example as we come across it. So the first derivative test using the sign graph gives us local extrema, as well as intervals of increasing and decreasing. Concavity and second derivative test, those are really two different things. Both of them use the second derivative, okay? The second derivative test give us half of the information of the first derivative test. That's why we really don't use that for graph. I will show you, but concavity is a must. Therefore, let's have a discussion on that. So f double prime or y double prime, if it's positive, the curve is concave up. And if it's negative, it's concave down. If it's concave up, in the vicinity of concave up, this is the location of a local mean. Okay, so when f double prime is positive, it gives us local mean. And when it's concave down, it gives us a local max. So, and of course, we have to find f double prime, where f double prime is 0 or doesn't exist. If the change occurs, for example, this is concave down, this is concave up. At the location of the change, we call it an IP, an inflection point. And of course, how do you find all of these? Concave up, concave down, inflection point. You have to use a sign graph on y double prime or f double prime of x. A function is considered concave up, where f double prime is positive. That means f prime is increasing. It was discussed. And it is concave down, where f double prime is negative or f prime is decreasing. Now, we want to graph this function, and to do so, class, before I go through the steps, calculus steps, I want to graph this, and I want to show you how this is done using the old method, okay? By that, I mean looking at what we did in pre-calculus. So let's do that. We are going to look at pre-calculus stuff, and we see how this is going to be graphed. First and foremost, if I want to graph this, I need my intercepts. So I hope you see that right here. I have negative 1, 0. Right here, I have 2, 0. So I have two of my intercepts. And I hope you see that that's the y-intercept. So we already have 3 points, easy points. Again, what is the x-intercept? Set y equal to 0. What is the y-intercept? Set x equal to 0. Refreshing your memory about that concept. Very simple. So we have those. The next thing I want to discuss is the end behavior. I hope you remember that the end behavior looks at the leading term. Okay, so leading term is in the form of a sub n x to the power of n. Okay, if n is even, it looks like y equals x squared if a sub n is positive. That means we are dealing with the first quadrant end behavior and second quadrant. If a sub n is negative, the graph looks like y equals minus x squared. Okay. What happens when n is odd? Okay. When n is odd, looks like y equals x cubed if a sub n is positive, and that means the end behavior, quadrant 1, quadrant 3. This is not to scale by any means. And if a sub n is negative, then we have the end behavior happening in quadrant 2 and quadrant 3. I hope everybody remembers that. Now, behavior near an x-intercept. So that's the first topic. We have minus 1, 0 with the multiplicity 1. By that we mean odd. Look at the exponent. The exponent that doesn't exist is 1, x plus 1 to the power of 1. On the other hand, if you look at 2, 0, the multiplicity is 2. And what matters is that it's even. So what is the difference? I hope you remember. When we have a odd multiplicity, the graph will cross the x-intercept at that point. When it's even, the graph cannot cross the x-axis, I should say. Not. So at that point where we get to the x-intercept, this is what happens. Now, let us graph this, okay, with the information mentioned. Okay, let us graph this with the given information. So I'm going to graph this, and it's not going to be to scale by any means, but we try. So we said we have minus 1, 0. We have 2, 0. And then we have 0. Now, what I want to do, remember at 2, 0, we have the multiplicity 2. We use this type of arrow in calculus, double arrow, meaning it can't cross that. And I'm going to put those 2 arrows referring to our end behavior because it starts with x cubed. So basically, the graph, if we start from here, comes down and hits this point, and it has to come back up. It can't penetrate, it can't cross the x-axis because of the even multiplicity. Now when it goes back up, okay, and I'm going to stop here, somewhere it has to come back down, okay. So where does it come back down? Let's say here, and it goes through the y-intercept, and then the next x-intercept, it crosses it, okay. Now here's the thing though, when and where do we come back? Are we looking at this one? Coming back down here? Or even here? So the problem is we don't have this information. It comes from calculus, but everything else basically done. So let's quickly do calculus, everybody, and finish the job here. So we already have a rough sketch of the graph, okay? So we have the intercepts. So what do we do next? It's very simple. Let's do the next step, finding y prime or f prime, okay, and see what happens. Y prime or f prime is 3x squared minus 6x, and we set it equal to 0 by factoring the 3x out. And we get 2 answers, 0, 2. And now we are going to do the first derivative test using a sine graph. So I want you to pay attention to sine graph and the way it works. Here's a number line from negative to positive infinity, x. We choose those critical points of 0, 2, and at top here we put f prime of x. At x equals 0, f prime is 0. At x equals 2, f prime is 0. So we want to know the sign for f prime in this, as we cut it into 3 pieces, to the left of 0, in between 0 and 2, and beyond 2. And all you have to do, pick up a test point. For example, if you pick up a test point here, To the left of 0, the easy point would be -1 as an example. So you can pick -1. And what happens is you put this -1 into either this one or the factored format. It's easier to put it in a factored format because we want the sign. In other words, we want to see it's positive here or negative. So if you plug in -1, makes this one negative, makes this one negative, negative times negative is positive. Now, in between, we pick 1, after 2, we pick 3, and when we plug in 1 here, makes this one positive, makes this one negative, the product is negative. 3 makes both of them positive, the product is positive. So those are the signs. However, here's another piece of information I want to share with you that is going to make life easier if you pay attention to that. If this one, each and every one of them has exponent that is odd, none of them is even, then if you calculate one of them, the rest of them alternate. But if it has an even one, it doesn't alternate, okay? So you can get, but just to be on the safe side, check with the test point. So what does it mean? It means increasing, where you see f prime is positive is increasing, decreasing, increasing. So where is it increasing? From -infinity to 0, union 2 to infinity, and it's decreasing from 0 to 2. That's one. The other one, I like to put these arrows because up and down, okay? That means increasing and decreasing. So as it changes from increasing to decreasing, take a look. It gives rise to a local max. As it changes from decreasing to increasing, it gives rise to a local mean. So local max at x equals 0, and you got to plug it into here to find the pair. We already have that, okay? That is 4. Local mean occurs at 2. Now you have to put it back into the original function to come up with the pair. We also happen to have that as 2, 0. Therefore, we are going to write the following. Local max is 4 at x equals 0. So how did you get that? This number goes to the original function y equals f of x. Local mean, 0 at x equals 2. And as I mentioned, increasing here and here, that means with the union. We really better say increasing here or here. That's the statement or. And of course, in between 0 and 2 is decreasing. This is the first derivative test. When you do the graph, you don't need to do the second derivative test. The only reason I do it is for the sake of application, so you understand how it works. The reason you don't want to do it for the graph, because it gives you half of the information. But what is the second derivative test? I want to explain that to you. When f double prime is positive, we have concave up. Remember, concave up looks like that, and it's a relative mean. If double prime is negative, that means concave down. Concave down, that means local max. So if this is y prime, this is the possible extreme values. We need to find y double prime. So we are going to differentiate this again. This is a simple case of 6x minus 6. Okay. And so what you need to do now is to plug in. Here's the second derivative test. You are going to plug in your the possible extreme values, your critical points that was found in the previous step, and evaluate the y double prime at those points to see if it's positive or negative. That's all. If it's positive, that means concave up, relative minimum occurs there. If it's negative, that means concave down, relative max occurs. That's really the meaning of it. So let's plug in 0. I hope you see when you plug in 0, you get negative 6 or negative. If you plug in 2, you get positive 6. So when you plug in 0, you get negative, and negative means what? Concave down. Concave down looks like that. This is the local max, everybody. If you plug in the other critical point, namely 2, it is positive, okay? And it's concave up, looking like that. It gives rise to a local minimum. So what did the second derivative test tell us? half of the information of the first derivative test. What is that? It tells us which is a local max, which one is a local mean. It doesn't even give us the intervals of increasing, decreasing. So what is it good for? When it comes to graphing, you don't need to do the second derivative test. It has a lot of applications because it's normally easier than the first derivative test when we get to the application, and I'll show you. But we can use it for concavity test, okay, to see if we have an inflection point and so on and so forth. So with that being the case, let's set that equal to 0. So we've already taken care of y double prime, set it equal to 0, and at x equals 1, f double prime or y double prime is 0. So we do the sine graph to see what happens. So we are looking for an inflection point. So we may have it at x equals 1. We don't know yet. We have to check it. So at x equals 1, y double prime is 0. Okay. Now to the left of 1, the easiest point would be 0. Okay. And if you plug it into y double prime, makes it negative. So over here is negative. Okay. Negative means what? Concave down. So in this vicinity is negative, so concave down from negative infinity to 1. If you pick a number to the right, the easy number would be 2, gives you positive. Positive means what? This is concave up from 1 to infinity. So you write this concave down from negative infinity to 1 because of this negative sign. Concave up because of this positive sign. Because it changes from concave down to concave up, because of the change, it doesn't matter how, concave up to concave down or vice versa, then at x equals 1, we have an IP or inflection point. What is the pair? Put it back into the original function. So at x equals 1, we have the inflection point. We plug in 1 into the original function. It's easier to do it perhaps here or here, whatever that works. If you put here, you get 2. Over here, you get negative 1 squared, which is 1 times 2 is 2. So the pair is 1, 2. That means we are ready to graph. We are ready to graph. Let's do that. All right. To graph this, here's the function. Here's the intercepts. Let's make a summary table of what we have found so far. The x-intercept at negative 1, 0. Here's it. The y-intercept, which happened to be a maximum, is at 0, 4. Here we go. And we draw this one because it's a max. That means it doesn't go beyond that. We have the inflection point, the IP or inflection point at 1, 2, right then and there. We also have the x-intercept of 2, 0, which is the minimum value as well. I hope everybody remembers that. So we're going to put that in there. And that's it. The reason we do the arrow again, we are telling our reader it can't penetrate, it can't cross the x-axis at that point. Okay, so extra point, you remember the end behavior is here and here. Okay, so if you want an extra point, you can draw that, or if you don't want it, it's really not that big of a deal. But if you want a more precise graph, I highly recommend you pick up a couple of extra points, one here, and because it crosses this, maybe 1 to the left of negative 1. So from here, we basically graph it like this. So it looks like that. This is the graph of the function.